Hey guys, welcome back to chapter 16. What we're going to do in this video is work through another example of calculating the pH for a weak acid. Here again is just that quick reminder of the steps that we're going to take. So write a balanced equation, draw an ice table and a Ka value, solve for concentration, then determine pH. So find the hydronium concentration and the pH of a 0.2 molar HNO2 solution. So this is nitrous acid solution where the Ka value is 4.6 times 10 to the negative fourth. So go ahead and pause the video, get as far into this as you can, hit play, and I will work it out with you. All right, so the first step is to get an equation onto the paper. So we need to first be able to visualize how this breaks down. So HNO2 is a weak acid. So again, we need to just make sure that it's not one of the big five. So it's not hydrochloric, not hydrobromic, not hydroiodic. It's not nitric. So nitric is HNO3. It's not nitric, and it's not sulfate or sulfuric. So it's a weak acid. A weak acid is going to break down via equilibrium. So we've got our acid. It's going to be in the presence of water. So our acid is always going to be a proton donor. So it's going to give away this hydrogen, which will leave it as NO2 minus nitrite. And then it's going to donate this proton to the water. So water will be H3O plus. Okay. Next thing is to get a Ka equation onto the paper. So concentration of our products over concentration of our reactants. So concentration of NO2, concentration of hydronium over concentration of HNO2. Oops, brackets. And this is weak, so we know we're going to need an ice table. So ICE. On the top is HNO2, NO2, H3O. All right. So this is really just setup at this point. I haven't put a whole lot of thought into anything yet. I'm really just kind of setting myself up for success. Now that I'm set up for success, I'm going to go back and read through the problem and start crunching some numbers. So it tells me that the weak acid is 0.2 molar. So that's going to be the initial concentration of our weak acid. And then we're going to assume, since there's no mention of the other two, that those started at 0. Change, if it started at 0, the only change that it can have is a positive change. So positive X. And this guy is going to change by the same magnitude, but it is going to go down. So our equilibrium looks like this. 2 minus X, X, and X. Okay. Now that we have at least something for our equilibrium concentrations, we can now take these values and plug them into Ka. And I'm just going to go to a new slide so that I have some room to work here. So Ka was concentration of our, concentration of our products over concentration of our reactants. So the Ka value was 4.6 times 10 to the negative fourth. Looking at our ice table, both of our products were just X and X, and our reactant was 0.2 minus X. So certainly you could go through and you could solve this using the quadratic equation. I highly recommend that you use the X's small approximation, so getting rid of any of the X's that are being added or subtracted. Oops. So that's going to clean this up to look like this. 4.6 times 10 to the negative fourth equals, on the top, X times X is X squared, and on the bottom, we're left with 0.2. To get X squared by itself, I'm going to multiply by 0.2, so those cancel. Whatever I do to the right side, I also have to do to the left side. So I'm going to come up here. We're going to have X squared equals 4.6 times 10 to the negative fourth times 0.2. We're going to have 9.2 times 10 to the negative fifth. Then to solve for just X by itself, we'll take square root of both sides. So X equals the square root is 0.0096. Okay. Awesome. What does that mean? What is X, right? So going back to our ice table, we have solved for X. And remember, the hydronium is going to be the equilibrium value of interest. So hydronium concentration at equilibrium is just that X value. So I could rewrite this as hydronium concentration is 0.0096 molar. And then the pH is just the negative log of that value. So pH equals negative log 0.0096. 2.01. Okay. All right, ask yourself, does this make sense? Yes. So we determined that HNO2 was an acid, a weak acid. So it makes sense that this is an acidic pH. Thinking back to the problem that we did right before this. So the problem before this had a Ka value that was times 10 to the negative 10. The Ka value for this one is times 10 to the negative fourth. So the smaller the Ka value, the stronger the acid should be. And again, we see that the pH is a more acidic pH than the other one. So just really reaching into that last problem and making sure that we have a complete and full understanding, that also does make sense for us. That's it for weak acids. The next couple of videos are going to be about weak bases. I hope you guys found this helpful.